Good afternoon. Exam 2, November 18. I'll let you know about the place. It's going to cover velocity, acceleration, and force analysis. I may add some topics of kinematic synthesis. I should see how much we can go over these topics, then I'll let you know about them. Exam 2. Closed loop. Any question before? You are allowed to have one equation sheet as a both-sided. All right, come on. Let's back. So we are we are going to synthesis or design a 4-bar mechanism. It should be crank rocker and we would like the rocker oscillates for 45 degrees, for example, in this problem. So when the motor is gonna run continuously, when the crank completes one cycle, the rocker should oscillate for 45 degrees. So this is what we want to design by graphical approach. And it's a mechanism with the timing ratio equal to 1, meaning that the time it takes going from this point to the other extreme point is going to be same as the point that you back from this extreme point to the starting point. So this is what I mean by timing ratio equals to 1. So I'm going to start from scratch. So if this is O2, if this is O, this is O4, this is B. So make sure that you are following the step because we are going to go further on this. Pick a point. It can be any point on the plane. So I pick this point. This point is the location of O4. So you are free to choose any point on two-dimensional. So I already located point O4. I have to locate point B, A, and O2. Draw a line with any, just draw a desired line. It can be in any direction. It can be this line, this line, this line. So it's up to you. So you can pick any line. I pick this one. On that line, just pick a point. I pick this point. You can pick any other points on this line. And label this as B1. Draw the second line with the angle of 45 degrees with this line. So if this is 45, draw this line with 45 degrees. from the other line. So now draw a circle with this center and this radius. So with this circle, with this center and this radius of B1, draw a circle. The intersection of the second line with the circle, we label it as B2. Connect B1 to B2 and extend that. Just extend the line. Then pick one point on this line and label this as O2. This point that you pick is going to be the location of joint O2. Then, with this center, I'm going to draw a circle. The center of circle is going to be O2. The diameter of the circle is going to be B1, B2. So if this is the diameter, B1, B2, I'm going to draw a circle with that diameter. So the diameter of this circle is B1, B2 at the center of O2. The intersection of this circle with this line, we call it A1. The intersection of this circle on the other side, we call it A2. Now we are done with the 4-bar mechanism. Our 4-bar mechanism has center of O2 as the joint of O2 at this position. Link A is going to be this O2 A1. A1 to B1 would be B, which is this guy. B1 to O4 is C, which is this guy. And O to O4 is going to be D, the ground. So this 4-bar mechanism with this link as a ground, crank, coupler, and rocker. So when the crank is moving from this position A1, the rocker is the coupler is gonna be the rocker is gonna be at the position of P1. So when it goes all the way to A2, this is gonna move from B1 to B2, which is gonna give us 45-degree angle. And when it's gonna back to A1 position, the rocker is gonna back to its starting position, which is B1. And we can continue the motion. One thing that you have to check before report the mechanism that you design, ratio criteria. The shortest link, you pick the you compare them and find the shortest link. The shortest link plus the longest link must be less than P plus Q, and shortest link must be A, based on your design. If it doesn't satisfy, the ratio criteria, if O to A1 is not the shortest, or summation of shortest plus longest is not less than the summation of other two links, what you need to do, you need to change the location of O2. Here you pick this point, then you have to change O2 and get the new values and check the criteria.
So we just change the location of O2?
O2 and try the new mechanism to see if it can satisfy crank counter criteria. Here you see, I said for this problem we are gonna have 5 free choices. How do I count 5? We are working on 2-dimensional, x and y. So I pick x and y direction of O4 as a free choice. So you can pick any x and y for O4. So you already use 2 free choices here. You can draw this line at any angle with the ground line. So number 3, the angle of line with the ground. So it can be at any direction. So 3 free choices already used. I pick point B1 along this line. It can be any point on this line. After you draw the line, you have 1 free choices here, which is going to be free choice number 4. It can be here or any other position or location on that line. So point B2, it's not free choices. You are going to draw a circle with this center and this radius. So you are going to get point B2, but O2 is going to be your last free choices. It has to be on that line, but it can be anywhere on line, extended line of B1, B2. Is that clear?
For the first 2 choices that you said?
The first 2, location of O4, X position and Y position of O4 is not limited. You can pick any X and Y for that. Number 3 is the orientation of this line with the ground, 1 angle. It's going to be number 3. Number 4 is going to be on this line. You are free to pick any point. Good. So let me go more deep on this. You design the mechanism, say, all right, the mechanism, you measure them, you measure this, and say the link A, which is our crank is O to A1. B is A1, B1, or A2, B2, they are the same. C is going to be O4, B1, or O4, B2, and D will be O2, O4. And you check them, and it's satisfying crank rocker criteria. So if you remember, for crank rocker mechanism, you can find the minimum and maximum transmission angle. What if I say I would like to have, if I add more restriction on this design, I would like to have the maximum transmission angle shouldn't exceed 135, and gamma mean shouldn't be, it should be greater than 60 degrees. Then, based on A, B, C, and D value, you can find gamma or mu mean. You have covered this. There is an equation for mu mean, and there is an equation for mu max, and you can find them. You find them and check if you're satisfying these two. If you don't, then you have to come and change some of the free choices such that it can satisfy this. So for example, you may need to change location of B1 and try again. So we will do that until we get until we can satisfy the design criteria. Everybody knows how to find gamma mean and gamma max, or mu mean and mu max for a given crank rocker mechanism. If you don't remember the equation, that's fine, but we have covered this before, so you can just look at the slides and you can find that equation. Any question on this? One more thing before I go through the next problem. So suppose here I say after you pick O4, I would like O2 located at the line passing through O4 parallel to the ground. So I would like O2 is located at this on this line. So you pick any point O4 and then you draw a line passing through that point, and you would like point O2 located at this line. What should we do?
You have to shift the whole angle to lines.
Which line? This line?
Yeah, both of them, like shift them to like the angle.
You have to
Your B2 would be on the horizontal line from the. If you make B2 on the horizontal line.
I just want to have O2 on that line.
So if you draw an angle between the horizontal line and B1, let's say, like you have to increase that angle until O2 touches that line, the horizontal.
That can be, I mean, for example, I change, I go, I pick this line, instead of this line, I pick this line,
Yeah.
and this line, then I pick this point as a new B1, B prime 1, find the other B1 here, which is going to be B2. If I extend them, if I connect them and extend them, the intersection can be location of O2.
But the line B2 is dependent on B1, right? Because
Yeah.
we have the construction of 45 degrees.
Yes, this is what we want to have.
Yeah.
This angle should be almost always 45 for this problem. Everybody can see how I can play with the free choices to satisfy the design criteria. I would like to have, I have restriction. I cannot move the O2 from the line passing through O4. So I have to satisfy this restriction. So I'm changing the location of this line to another position, such that it's going to give me a line crossing line O2, O4. And the intersection is called O2, draw a circle with this diameter and this center.
So it would be better to draw the line first because you want them at the same level, right?
Yeah. Since I had this one here, I drew that. Yeah, but it's better that you draw one first, then start. Question on this. This slide is showing the steps. You pick a point, O4, any point, draw this line at any desired angle with the ground line. Pick a point, and this line, it can be any point, draw a circle or part of the circle with this center and this radius such that it gives us the intersection of the line, sorry, the circle with the other line. The other line has the angle of 45 in this example. Connect B1 to B2, extend, pick a point, any point, it's going to be the location of O2. Draw a circle with this center and diameter of B1, B2. So then you have O2, A1, B1, O4, which is going to give us our mechanism. But you have to always check for the Graphical criteria and crank criteria.
So, are we going to be given the measurements like A, B, C, D, or we have to find that?
No, you are gonna design the mechanism. We don't have anything. you should report for this. If I want to generate that desired motion, the A should be this length. So D should be that length, and C is this guy, and D is going to be this.
So the only
It's not going to be identical for everyone. So it's going to be different depending on your resources. So and some other.
So all we know is that what desired motion we want to get out of the mechanism. Right? And based on that, we design.
On this problem, yes, I would like to design a crank rocker first. It should be crank rocker. It should be 4-bar mechanism. It should be crank rocker, and the rocker should oscillate for 45.
Okay.
All right, now that was an example for function generation, because we were given with the desired motion, which has a relation between or correlation between input angle and output angle, which is the angle of rocker. So now we are gonna look at motion generation. So here, before I go further, so this is the mechanism that we designed for that. So this is O2, this is A. Link B should be between these 2 points, but it shouldn't be necessary as a straight link. It can be something like this. It's not going to change the motion of mechanism as long as you have these 2 points fixed. So I can have something like this. And this is going to be link 4. This is location of O4, B, A, and O2. So let's talk about the motion generation. Motion generation for 4-bar mechanism. Suppose this is C. I have the rigid body of CD. I would like to design a 4-bar mechanism such that it's moving rigid body CD from this position to this position. So this is what I would like to have. And CD would be my coupler in this case. So it's going to be connected at point C and D. But it's not always the case. The position of the joint can be any point on this line. But in this case, I would like to have the location of joint C and D at these 2 ends. So it's a motion generation because we are given with the motion of rigid body. Make sense? What we are going to do. So joint O2, which is this, wherever it is, it has the same distance from point C1 and C2. True? Because when I fix this and when the mechanism is moving from this position to this position, the length of the link is not going to change. It's going to be A, whatever it is. So it tells me point O2, should have same distance from C1 and C2. So if I connect these 2 points and draw the perpendicular bisector of C1, C2. So this line is the perpendicular bisector of C1, C2. perpendicular to C1, C2, and is passing through the middle of the C1, C2. Any point in this line has this specification. It has the same distance from C1 and C2. So you are free to choose any point on this line. I pick this point. You can pick this point. So I'll pick this point and fix it as a O2. So then O to C1 is gonna be A. Or O to C2, they have the same length. You can pick any other point here. Now, finding the O4, it's same as O2. O4 should have the same distance from B1 and B2. So I connect these two, draw a perpendicular bisector. Pick any point in this line. I pick this point and label it as a O4. Connect to D1. Now I have a mechanism with O2 C1 equals to A, C1 D1 is B, O4 D1 as C, and O2 O4 as D. And I'm done with motion generation for 2 precision points. We are given with 2 precision points. I would like to generate these 2 precision points. Any question on this? How many free choices did I make? 2. I draw this line, but I can pick any point in this. So it's going to be my first free choices. On this line, I can pick any point on that perpendicular bisector. So it's going to be 2 free choices. And now, this is the mechanism that I designed. O2, C1, D1, O4. So this is the mechanism. I suppose this is a crank rocker mechanism. I assume it's a crank. Such that if I put a motor here, it's going to run the mechanism. For sure, it's going to move this link from this position to this position. But this link is going to see the other position as well. But I would like to restrict the motion of mechanism only to these 2 desired precision points. So I would like to come out with a mechanism such that it's going to give me this desired motion, and also it's going to restrict the motion only to these 2 positions. I don't want to pass, I don't want this link is going to pass this position or this position. Make sense? The next step. We are going to add a diode. Add a diode. How can I do that? I'm going to combine this example with the previous example. So how can I do that? Just look at this link, for example, link 2. Link 2 is supposed to move from this position all the way to this position. So if I design a crank rocker mechanism such that the rocker is this guy, the crank rocker mechanism should be limited, the rocker should be limited to this angle, from here to here. And now we know how to design that crank rocker mechanism. So O2 is here, it's a location of C2. C1. So it's going to be the new rocker of the rocker of my new mechanism. Pick any point on this line. I'm not gonna. I don't have any free choices on O4, which is ideal O4. I have no free choices. I'm picking this line, but I have free choices. I'm picking any point on this line. I pick this point as a B1. Pick the corresponding point here by drawing a circle with this center and this radius. So I will find P2. Connect these two, extend them, pick a point here, and label that as a O6. O6. O6 is the location that I'm going to put the motor here. Draw a circle with this center and this diameter. This is going to be A1, this is going to be A2. Now, the mechanism that I designed, O6, A1, A1, B1, B1, O2, and O2, O6. It's a 4-bar mechanism. First, we should check the Graphical criteria. If satisfying the Graphical criteria and crank rocker, then I can make sure that if this guy, if O6A1 completes 360 degree B1, it's going to go from B1 to B2, and it's going to back to B1. And this is how I can restrict the motion of the mechanism. One group can pick something like this to find the application for that and design. It's a 6-bar mechanism. Diode is four, and the other 2 links is gonna change it to 6. So this is how we end up. This is O6. It's this guy. This is A1. Then B1 is gonna be here, and I chose B1 this. Into this, the slide has B1 and B2. So when it's running, it's gonna move the rocker. It's gonna move the rocker from this position to this position, and this mechanism is gonna move C1, D1 from this position to C2, D2. Any question on this? Yes.
Is it possible to use a binary link instead of a ternary link?
There.
Like the link O26.
O2, O6.
O2 to C1.
Yep. It's
Is there like an advantage of having
no, it's a straight line. I mean, we just add a joint here to make it ternary links. So you are talking about the shape. The shape, it doesn't matter how it's gonna look like. I just showed you on the previous slide. If I want to connect here, if I have a binary links from this joint to this joint, it can be a straight, or it can have any other shape. What is important is it has 2 nodes, which it has been connected to the other link. So this is the ternary because it has 3 joints. Here I added the diode to this link. Can I add it to this guy, to O4 B1? We can. I can do that. If you want, it's just gonna have a different lines, and this joint and this joint should be moved to the link O4 B1 and O4 B2. So that one is the motion generation with 2 precision points. Now we are going to move to 3 precision points. Any question on this? Suppose I have link or rigid body AB. I would like to move it through these three precision points. Through A1, from A1 B1 to A2 B2, and the third one is A3 B3. We are given, it's a motion generation because it's talking about the motion of a rigid body. So we know that it's motion generation. And it's three precision points because we are given three desired locations. I'm going to repeat the steps again. A1 to A2. Find the perpendicular bisector. Wherever is the location of O2, it should have the same distance from A1, A2, and A3. So I know that O2 is going to be on this line. At the same time, I know that the O2 is going to be located on perpendicular bisector between A2, A3. So intersection of these two lines is going to give me the location of O2. So basically there is no free choices left for me. You might say, why didn't choose A1 and A3? We can prove that if we draw A1 and A3 and draw the perpendicular bisector, it's going to pass through this point. So we don't go through to prove that, but it's true. So this is the location of O2. So if I connect this to this one, I'm gonna get O2 to A1. It's gonna be the A. It's gonna be B. I should find the location of O4. I connect B1 to B2, draw the perpendicular bisector. B2 to B3, I wish let me change it. Just a little bit. O4. So this is A, this is B, this is C, and this is D. So this mechanism is going to move link AB from this position to this position and this position. Here you can see a better drawing. I have A1, B1, A2, B2, and A3, B3. I draw the perpendicular bisector between A1 and A2 because I know that O2 should have the same distance from A1 and A2. At the same time, it should have the same distance from A3. So I draw the perpendicular bisector of A3. The intersection is going to give me O2. Repeat the steps for O4, but this time I'm going to use B1, B2, B2, B3. And as I said, we can draw the line between B1 and B3 and draw the perpendicular bisector. It's going to pass me through the O4. So this is how you can find O2 and O4. Question on this before we do a class activity. what if, just saying on the two precision point, what if I wanted to restrict the motion of the mechanism between these three precision points? I have a 4-bar mechanism, O2, A1, E1, O4. And I'm sure that it's gonna give me these three precision points. But I would like to restrict the motion of the mechanism between these three. What should I do?
You want to try it again?
How can I do that? Which lines?
So your two extremes will be A1 and A3. O2, A1 and O2, A3.
Exactly. I should add a diode such that the rocker has the restriction of moving from O to A1 to O to A3, or O4B1 to O4B3. Either way, if you want to have a diode on these two links and on this one, you can use O to A1. If you want to have a diode here, you can have O4B1. So pick these 2 points. No need to do the lesson. So this is O to A1 and O to A3, the two extreme position of link 2. Pick 2 points. Pick 1 point, C1. Draw a circle with this center and this radius. You are gonna get C3. Connect C1 and C3. Extend. Pick 1 point, which is gonna be O6. And on that point, just draw a circle with this diameter. And you will find the location of the diode. Here I will label it as a T. And you can restrict the motion between these two. Any question on this? Yes.
So the position of the must it be between D and the middle? Or can it be between any of the three?
Say it again.
DC3 must
DC3. Okay.
must it be between D and the middle?
No, this, I mean, D is here. When D is here, it's gonna be at C3, okay? When it's moving to this position, it's gonna move to C, to this one. And then when it's back to this position, you are gonna be at this position. I just wanted to show you how this mechanism is moving. So you pick these 2 points. No, it doesn't matter which point is going to give you the middle. Because we just want to restrict the motion between C3 and C1. Alright. Now it's time to talk about the quick return mechanism. Oh, I forgot to bring the mechanism. I'll bring it tomorrow. So suppose this is a mechanism for the cutting tool. So you add the cutting tool at the on this machine. When it's moving from right to left, forward motion, it's gonna remove the material from the surface. So it's gonna remove the material when it's moving from right to left. When it's moving from right to left, since it's doing some job, it's removing the material, it should move slowly. So just the slowly motion. So, but when it's gonna back to the starting position, it doesn't do anything. So just going back to the starting position to start the job again. So on the backward motion or return motion, the speed can be faster. So we would like to design a mechanism such that it's, for example, provides us a mechanism with timing ratio of 3. What does it mean? Speed of velocity of backward over velocity of forward is 3. So backward motion, which is left to right or return, is going to be 3 times greater than the forward. One group picked this one as a project. If any group is interested, they can work on this one for different timing ratio. So timing ratio depends on your interest. So depending on what you want, you can specify the timing ratio and then design your mechanism such that it generates this desired timing ratio. So let's back to this diet problem, to this crank rocker mechanism. When this crank is moving from this position to this position, the rocker is moving from B1 to B2. And on the backward motion, it's moving from A2 to A1. It's moving from B2 to B1. So as you see, this angle is 180 degree for forward. And on the backward also, it's going to be 180 degree for backward. It tells me the speed of forward motion, how many seconds is going to take from A1 to A2, is going to be the same as the time it's going to take from A2 to A1. So same here. From B1 to B2, it's going to take the same time from B2 to B1. So here we have timing ratio equals to 1. But what if I want to design a crank rocker problem with something for timing ratio different than 1? 3.2, 2.5, 1.2. How should I do that? We will go over this tomorrow.